Hey folks, welcome to our newest lesson about trig functions. So today we're going to look at our inverse trig functions. So I have this question, what does this mean again? Okay, what does the arc sine of x mean? Remember, so we can write it as the arc sine of x, remember, or there's another way to write it. And you can write it as this, which we read as the inverse sine of x. We don't rate it, it's not a negative first power, it's just a notation saying that we're taking the inverse of our sine function. So what does that mean again? Okay. Well, if we go back to our definitions that you guys would have learned probably back in geometry, if y equals the sine of theta, then theta equals the arc sine of y. So it's an inverse, which allows us to reverse the operation. Just like the inverse of squaring something is taking the square root, the inverse of taking the sine of an angle is to take the arc sine of the ratio. So just a reminder here, so this is our angle, and that's our trig ratio, right? Sine is opposite over hypotenuse, it's a ratio. So the sine of an angle is equal to a ratio. The angle is equal to the arc sine then of the ratio. Oftentimes I like to say it, I would read this, the arc sine of y, as the angle whose sine is y. Remember that arc sine, just like arc cosine and arctangent, they allow you to solve for the angle. The arc sine is equal to the angle. So my phrase again, arc sine of y is the angle whose sine is y. The angle whose sine is y. We would define arc cosine and arctangent similarly. If y equals the cosine of theta, then theta equals the arc cosine of y. If y equals the tangent of theta, then theta equals the arc tangent of y. Now, how have you used this in the past? Well, if I were to draw a triangle, such as this, and I'll make it a right triangle, and we'll put theta right there, and let's say this is 2, and let's say this is 5. Now, I want to know what that angle theta is. Well, I would say the sine of theta, because this is opposite and that's hypotenuse, the sine of theta equals 2/5. So how do we find theta? Theta equals the arc sine of 2/5. And then I can grab my calculator, and let's see here, my mode is in radians, and I can type in the arc sine. Now that is the sign with the negative first there, the second notation of writing it. I typically, when I'm writing it on paper, I like to use arc, even though our calculator uses that -1. So I'm going to take the arc sine of 2/5, and it gives me theta equals 0.411. Okay, and that would be in radians. Or I could switch my mode to degrees, type in the same thing, and it gives me, or about 20, this should be an about sign because we're rounding, about 23.58 degrees. So that's how you're familiar with working with your inverse sine, cosine, and tangent. Okay. Now let's evaluate the arc sine of 1/2. So again, the phrase that I'm using is I want to find the angle whose sine is 1/2. Now I know I used my calculator on that last example, but let's go to our unit circle here. The angle whose sine is 1/2. Okay, so I'm going to look at my unit circle and I'm going to try to determine where is the sine equal to 1/2. What angle has a sine equal to 1/2? And what we see right here is at pi over 6. Okay? So I might say something like, well, the sine of pi over 6 is equal to 1/2. So that tells me the arc sine of 1/2 equals pi over 6. Over 6. But then I start looking at my unit circle some more, and I realize something. There's another place. There's another angle, hey, whose sine is 1/2. It's right here. It's at 5 pi over 6. Isn't the sine of 5 pi over 6 equal to 1/2? So that also tells me the arc sine of 1/2 could equal 5 pi over 6. So how do we handle this? How do we handle that there's two of them? And actually there's more than two. How many are there? There's really infinitely many, because I could say, well, it's pi over 6, or I could do one full revolution of 2 pi and then a pi over 6. So that'd be what, 13 pi over 6, right? There are infinitely many angle whose sines are 1/2. So how do we handle this? You should be keying in on something right now. If there's more than one y value for each x value, this is not a function. Okay? But let's think about what the graph of f of x equals the arc sine would look like. Now, we're talking about inverses here, and we've studied inverses a lot, so we should be keying in on a few important things about inverses. So what are some reminders about inverses? Their x's and y's switch, which means their domains and ranges switch. Their reflections over the line y equals x. So if I want to determine what does the graph of f of x equal the arc sine of x look like, let's graph f of x equals the sine of x, and let's just reflect that thing over the line y equals x, okay, by switching the x's and the y's. So let's go to Desmos. And let's graph f of x equals the sine of x. Let's see here. In the way. All right, where should I be? Let's put me over there. Let's grab a picture of this. There we are. All right, so in the red, should really make red one of these colors, although I've been really digging the orange, blue, green, and pink options, but we'll just write it in pink. Okay, so this red graph is the sine of x. So let's take and let's reflect this in the line y equals x. Let's see here, line y equals x would be right there. And let's reflect some points. All right, 0, 0. Well, that would be 0, 0. Let's pick a nice point here, right here. That point, what is that point? That's pi over 2 comma 1, right? So when we reflect that over, that becomes 1 pi over 2. So 1 pi over 2 would be the same as this x value, just as a y value. So that looks like it would be right about there, which looks appropriate that got reflected over. Okay. Now let's take another point. Let's take this point right here. Okay, that's pi comma 0. So we're going to go 0 comma pi. That'd be maybe right about there. Now let's take another point, this point right here. This is at 3 pi over 2, isn't it? 3 pi over 2, negative 1. So we'd be at negative 1. 3 pi over 2 is just short of 5. Okay, looks about like that. Yeah. These should be a little bit more evenly spaced. Am I off on one of these? That looks good. Pi. Just wonder if this should be a little bit closer. Make it a little bit more evenly spaced like it's supposed to be. I think that's supposed to be a little bit further up. There we go. All right. Now what do we have right here? We're at 2 pi, and we're back to 0. So 2 pi 0 is going to become 0. 2 pi is right about there. Now, if we continued and we went backwards, okay, we would be at negative pi over 2, negative 1. So it'd be negative 1, negative pi over 2, which would be right about there. That's the reflection of this point in that line. Then we would be at negative pi 0, so we'd be at 0, negative pi. We would be at negative 3 pi over 2, 1, so that'd be 1, negative 3 pi over 2. And then back here we would be at negative 2 pi, 0, so that'd be 0, negative 2 pi, which is down here. So what's this graph look like? Okay, you probably spotted this coming. Maybe even before I started graphing these points, or maybe after I first started graphing a few of them. This is not my best graph. Kind of close, but you get the idea, right? And these are just going to continue going up and down. Now, I said something on this slide right here. I said, you know what? There is more than one angle whose sine is 1/2, and we can see that here when we go to this graph, because if I pick 1/2, which would be right here, okay, how many places is that intersecting our graph? I did not do a good job. This would keep going that way. It would hit there again. I did a poor job down here. This would go that way. Okay. But we see that there are multiple places, okay, where if we put in 1/2 into our function, f of x equals the arc sine of x, there's multiple y values. Now, I just said something totally wrong. Okay, if it's a function, there can't be multiple y values. This is not a function. So here's what we do. We have to restrict the range of this so that it is a function, so that each x value only has one y value. Now, where could I do that? You know what? I wonder if putting up some rectangles would be helpful. Let's do that. And let's shade it in here, maybe white. All right. Let's make a couple rectangles here. So let's see here. If I cut it off at 0, and I cut it off up there at 3 pi over 2, that's still not a function. It fails the vertical line test, doesn't it? Where could I start this and where could I stop it? Well, if I put it there and there, now this little section right there passes the vertical line test, but that's also starting above the x-axis. The places that we like to cut it off at are actually right here and right there. That little part right there is a function. It passes the vertical line test. If I slide this rectangle up a little bit, it's hooking back over and it fails the vertical line test. Same if I were to slide this one down just a little bit. Okay. This should be hooking back in here. I didn't do a great job graphing it, but it would fail the vertical line test. So what we like to do is we like to cut it off there and there. And this orange graph right here is how we define the arc sine. Okay? And if I go back to Desmos and I type in f of x equals the arc sine of x, you will see just that little graph. So I'm going to wrap up our video on this one. You continue to learn more about arc sine, arc cosine, arctangent in the next video.